So in 4.2, we found the area underneath the curve using left and right endpoint rectangles. Now, to get a more accurate answer, we can go ahead and use a midpoint rectangle, which is where the top center of the rectangle touches your curve. But for the most part, it could actually be touching your curve at any spot. Doesn't really make a difference. The Riemann sum is really the process that we started yesterday. Now, remember when we were dealing with the first couple of units here, when we were dealing with left endpoint, we started out with I equaling 0 with our sum to the n minus 1 of your function. Now, for the most part, these are all off by 1 with what they're saying here, so it doesn't really make a difference. Your right endpoint we always had starting at 1. Your midpoint would be slightly different for figuring out x sub or m sub I, the middle of it, and you would go ahead and use this here. Now just to go ahead and review what we learned in the first couple weeks is that any area above the curve is a positive area because you go to the right, which is positive, and your height is positive. Any area below the curve, it is negative because you'd be going to the right, which is positive, but your height would be negative. So if we're looking at our definite integral from a to b of your function, we'd be looking at all the area underneath your function between a and b. We looked at the limit process yesterday. Now, there's two ways to look at this. We looked at it as the number of rectangles going off towards infinity. You could look at the number or the width of your rectangle going towards 0. So it can be done either way. So we would say that a is your lower bound, b is your upper bound. And the variable on the inside needs to match the variable after your d. But it doesn't make a difference really what variable you're dealing with. It should work either way. So the dx is called your integrand, or the du, or your dt, whatever you want to call it. So let's go ahead and consider this integral. We'd be looking at our area between a and a. A is the same thing, so you're looking at the area in between the same number. Well, there is no area in between the same number, so it would be 0. Now, if you go ahead and take your bounds and switch the order, you really get the opposite of your area. So if you switch your bounds, you get the opposite of your area. So let's go ahead down below here and work out our area of this using the same process we did yesterday, with 0 being your lower bound, 4 being your upper bound. So the helps you with figuring out the x. So we get 4 over n. Remember, x sub I is your beginning, which in this case is 0, plus I times delta x that we just figured out to be 4 over n. In other words, we get x sub I just to be 4i over n. Your function here is input cubed, which is x sub I, minus 2 times your input, which is also x sub I. So if we can take our x sub I right here and plug it in for each one of our x sub i's. And we could plug in our delta x, which is 4 over n. We cube the top, cube the bottom, get 64i over, oh, I see we got a typo here. So this should be over an n cubed. And this should be over an n to the first. So now we could go ahead and distribute that in. And so your n times n cubed is your n to the fourth. your n times n to the first is n squared. We could apply that summation to each one. So I'll take the sum of the first one minus the sum of the second one. You now have numbers in black times an I cubed. So you could pull those numbers in front and have the sum of I cubed. Here we have a 32 over an n squared times your I. So we could pull that black in front and have it times the sum of I. Well, we have a formula for the sum of I cubed. Then remember you have two options. If you know what n is, you use the first option. If you don't know what n is, which in this case we don't, because n's going off towards infinity, you use the one with separate fractions. And these go back to your formulas from section 2. We also would then have the formula for the sum of I. So at this point, all we'd have to really do is distribute here and distribute here. Distribute through, distribute through, distribute through. Distribute through over here. And then you're looking at the sum of this with n going towards infinity. Well, if anything that has an n in the bottom, because n's going towards infinity, getting really big, all those fractions go to 0. So it's 64 plus 0 plus 0 minus 16 minus 0, so we get 48. So let's go ahead and evaluate one more thing. Let's go ahead and take a look at evaluating y equals x. So just x is our function from a to b. So we're still going to go ahead and figure out delta x, the big one minus the small one, over n. And the beginning is a. Now we have to take our function, which is just x, so that's x sub I times delta x. Now, for the sake of what we're going to be doing right now, to make it a little bit easier, instead of plugging in delta x being b minus a over n, I'm going to leave it as delta x right now, and we'll plug that in a little bit later. So I could go ahead and distribute through my delta x, and I would get this. So over here in the second part, I have delta x times delta x, so it's really a delta x all squared. So we have this. It's a delta x really times a 1. And then we have a delta x squared times an I. We can apply our summation to each part. Take the sum of the green plus the sum of the black. We now have stuff after our summation, the a and the delta x, that we could pull in front of our summation. And then we'd have the sum of 1. And you should remember that the sum of 1 is n. And then over here, we could take delta x squared, pull that in front of our sum, and then we just have the sum of I. And you should remember that the sum of I is this. So we have the exact same thing here. I just changed some colors. All we're going to do now is plug in what delta x was. Remember, delta x was right here. We're going to replace our blue delta x with b minus a over n. Replace this delta x with b minus a over n. So over here, your n on top and on the bottom, they're going to drop. You just have a times the top. Over here, I'm going to apply the squared to the top, squared to the bottom. This first part we'll just leave alone for right now. Now I'm going to write this as b minus a all squared. Instead of dividing by n squared, I'll multiply it by 1 over n squared. So now all I have to do to simplify this is take this right here and distribute it through. So Didn't do anything there to begin with. Distributed that green fraction through, we get this. So we're looking at n going towards infinity. Well, there's no n's here, so it has no effect on that. N going towards infinity, there's no n's here. Here, 1/2 has no n's, but this has an n in the bottom, so that goes to 0. So you have 1/2 plus 0. Now, I'm going to go ahead and distribute through my a. It's 1/2, and then I'd have to FOIL this out. b minus a times b minus a. Distribute through the 1/2, and then I could collect my like terms. You notice here ab minus ab, they're going to cancel. You have a 1/2 b squared. You have a 1/2 a squared, and you're subtracting a 1 squared. So you get a b squared minus a 1/2 a squared. Here, we would have a horizontal function, constant function, and you'd be looking for your area underneath that curve. Well, that would then be just basically a rectangle. So there's times we don't have to use the limit process, and we can use geometry and do our width of 2 times our height of 4 and get 8. This, you know, is a diagonal line. You'd be looking at your area between 0 and 3. So in other words, that ends up being a trapezoid. And you could use the area of a trapezoid. 1/2 your height, which is the distance between the two parallel sides, and then the length of your first parallel side plus the length of your other parallel side. Or this one here, this is a semicircle, top half of the circle. You're looking for your area between -2 and 2. Your radius is 2. Well, if we pull up our semicircle, you would know that area of a circle is pi r squared, but we're only dealing with half, so it's half times pi r squared, and you get 2 pi. So sometimes you can use geometry, and other times you have to use the limit process.